Welcome back. So, we're sort of coming to the end of the class, and I'm going to spend the last two videos sort of wrapping things up and talking about a couple of concepts that I think you need to know before you finish quantum mechanics, in case in your life you come across some problems in quantum mechanics where our standard methods of solving the eigenvalue equation for the Hamiltonian is either too hard or takes too long, or maybe even not precise enough. And so what we're going to be working on are two ways of approximating solutions to the eigenvalue equation for the Hamiltonian. Our goal is the same, right? We want to find out what the energy states are, or at least an energy state. And then we're going to use that energy state to do things like spectroscopy or whatever, right? But it's still the process of trying to identify some information about the eigenstates of the Hamiltonian operator. So let us remind ourselves of the real way, or the old way, or the traditional way, or the purest way, right? I start with the eigenvalue equation for the Hamiltonian, h psi is equal to e psi. And then generally, if I'm working on a problem where my potential is a function of space, it's easiest for me to go into the position basis, right? And I write down this second order differential equation. And that second order differential equation is still an eigenvalue equation. But I look for independent solutions, and then I apply boundary conditions that quantize the system. And then I get out the eigenstates and the eigenvalues, right? And I have certain amount of use for both the eigenstates or the eigenvalues, depending on what kind of questions I'm asking. But whenever I do this, right? So one of the consequences of having this set of eigenstates is that there's always a lowest eigenstate, right? There's always especially in bound state problems, right, where that is perhaps the most important. I always have a state that has lowest energy. We've been calling this the ground state, right? The lowest possible energy. And an interesting property of that is that it sort of sets a standard, or it's a special kind of state for us, because any state now, if I do things like calculate if I let me start by decomposing my state onto the real eigenstates of this problem. I can do this, remember, whether or not I know what the eigenstates are, right? I know that I always can decompose it onto the eigenstates of the Hamiltonian, and then I have a set of probability amplitudes, which again I'm going to call alpha sub n. I can use this idea to calculate things like the expectation value of the energy. And so now this is why the lowest energy state is an important ingredient at this stage. Because if I take the expectation value of any state, then that is really the expectation that's equal to a sum over the energies of those states times its probabilities, right? And that should be a probability there, right? Which means that unless my state is totally in the ground state, it's going to be made up of pieces, right, that have higher energy than the ground state. And therefore, the expectation value of the energy can only be as small as the ground state. And in fact, it will always be greater than or equal to the energy of the ground state. Okay? And that's the concept that we need in order to do this first approximation method. We have to know that the expectation value of the energy of any state is bigger or equal to the energy of the ground state. And once I'm happy with that, well, then I can say, this is what I just said. The expectation value energy of any state is greater than or equal to the the energy of the ground state. Once I'm okay with that, well, then I can say, well, let me just make up a state, right? And if I can calculate the expectation value of the energy of that state, I know that it's still going to be bigger than the energy of the ground state, or equal to. Okay? And so here's the trick. Here's our new method. We're going to guess a state, a nice state, a state that's easy to integrate, perhaps, or a state that looks like a ground state-ish thing. Like a common thing that we choose is something like a Gaussian, or perhaps a witch's hat, or some. You choose some wave function that should minimize how hard it is to do the problem. And then you calculate the expectation value of the energy. And now, generally, right, sometimes we calculate expectation values by, projecting my state onto the eigenstates and summing up over the probabilities of being each one of those states. But I can also calculate the expectation value of the energy just by brute force, right, by using Griffith's rule. And if I use Griffith's rule to calculate the energy, I don't actually have to know what the eigenstates of the energy are before I start the problem, right? I can just calculate the expectation value of the Hamiltonian, and I can get the energy of this state. And if I get the energy of this state, I know it's going to be greater than or equal to the ground state energy. But the thing that's hidden here is that when I guess this wave function, when I guess what this wave function should look like, I'm going to make sure there's some variable in it that I haven't specified yet. So in the case that I'm looking at here, that variable is the width. It's the sigma of the Gaussian, right? And therefore, when I calculate that expectation value, I still have some freedom after I'm done because I don't know how wide the Gaussian was before I started. Okay? Which means that the energy of my state actually depends on that parameter, right? So I guess we could properly call it's a one parameter family of functions or a one parameter family of Gaussians. It's a wave function with one unknown. And so if my energy depends on that sigma, then a good choice of sigma should be able to minimize the energy of that state. Okay, and literally what we're going to do is we're going to calculate all of these integrals. We're going to calculate the expectation value of the energy, and then we're going to take that function and minimize it. And we'll know that the minimum of that function is still going to be greater than or equal to the energy of the ground state. But maybe if I guessed well enough, I'm going to get an energy that's close enough to the ground state for me to do the physics I need to do, or to guess the scale of the problem, or to know that the ground state exists. Okay. And so when we minimize this and find the lowest possible energy, we're really doing something about, doing our best or something, or minimizing our work to get a good approximation to what the ground state should be. And again, this works best in problems where solving these eigenstates is really just too hard, right? But yet you need to know, say, the binding energy of helium, right? Or you need to know you need to know what the ground state is for some particular question. Okay, so to show you, I'm going to do an example, and it's a hard example, right? But it's also the example that we've gone to so often to prove why hard things are hard. Let me give you the example of the finite square well. Okay, now we know that the solutions to the finite square well are not Gaussians, right? The ground state of the finite square well does not look like a Gaussian. It looks like sort of a sine in the middle and then a decaying exponential on both sides. We've done that problem. But let's use this method and say, well, what if it kind of looks Gaussian-ish? Can a Gaussian approximate the energy of the ground state here? Okay, and so again, I'm going to use Griffith's rule, which means that to calculate the expectation value of the energy, I have to squeeze the Hamiltonian in between a psi star and a psi and integrate it along the entire domain, right? Which means replacing the Hamiltonian, and I get this beautiful expression that gives me the sort of kinetic energy contribution to the expectation value of the energy and the potential energy contribution. And again, these things aren't easy to do, but they're integrals that we can do, or at least I put them into Mathematica and they did them, right? The kinetic energy is something that I can do from minus infinity to infinity because that, the second derivative of the Gaussian is very well defined. And in fact, the integral that we get out is really, something that we can look up in a table or something we can do in Mathematica very easily. The contribution to the potential energy, again, I have to do it piecewise, right? Because in the middle, the potential energy is 0 and there's no contribution, but outside the potential energy is equal to V naught, right? And there should be a V naught. There should be a V naught here, right? I get that there's two contributions to the energy. Okay, so what we see is that at least the first step of this process is done, right? The first step of this process is pretty easy. So what's left is I have to minimize this function, right? I have to minimize it with respect to sigma to try to find out what with Gaussian does the best job at estimating the ground state. Now for that, I'm actually going to switch over to Mathematica. Okay, we're going to start by just evaluating this wave function that I showed you, right? So this is the Gaussian. It's centered at 0 and it's normalized, right? I guess to convince you it's normalized, we can actually go to this line and show that psi star psi, I'm leaving out the conjugates because the wave function is real, but the integral of this over from minus infinity to infinity is indeed 1, right? So then I can come down here and I can start to calculate things like the kinetic energy. And the kinetic energy is minus h bar squared over 2m times psi star times the second derivative of psi with respect to x. And again, I want to integrate that over all space. That's the first integral that I showed you on the previous slide, right? And note that this is some sort of simple answer, right? And that's beautiful, actually. It's also neat to note that the potential doesn't show up in this term. So if you're ever using a Gaussian test function for this method, this is always going to be the kinetic energy of it, right? Of course, it depends on sigma, but this is always the contribution to the energy from the kinetic energy. Now, for the potential energy contribution, I need to do psi star psi times V naught, right? But I only have to do it in regions where V naught is not equal to 0, or where V is not equal to 0, which means that the left-hand side from minus infinity to minus A, and the right-hand side from A to infinity. In the middle of the well, the potential is equal to 0, and 0 times the integral is not going to contribute. So I can do those as well. And here you can see I come up with these error functions. These shouldn't scare us. They really aren't errors. They're just integrals of Gaussians, and it's something that Mathematica knows, and it's something that you can look up in a table. But it's just a named function that generally comes up as we're doing this sort of integral. Okay. So the energy is the contribution of those three things, and that you saw on the slide as well before. But let's just plot it, right? Before we start to do the minimization, let's plot it, and again, I'm setting most of the things equal to 1, but I want to see what happens to the energy as we change sigma, right? And look, this is kind of neat. Now, for sigma less than 0, perhaps this doesn't mean anything, but for sigma greater than 0, it does. And we can see if sigma is really small, if it's a really tight little Gaussian, then it's all sort of in the middle of the well, of course, but then the kinetic energy contribution is really big, right? Because the smaller I make sigma, the bigger that contribution from the first term is. And then as I make sigma bigger, the kinetic energy goes down, right? But then what starts to happen is more of the wave function appears outside the middle part of the well, and therefore the potential energy starts to contribute more. And so it's always a balance between how much kinetic energy you have and how much potential energy you have, which now, like, this actually makes, this method, as approximate as it is, gives us some intuition for how to build the right size function, right? And you can see that there is a minimum here, right? And that minimum appears to be around 1. It's probably not exactly at 1, but it's around 1. And so how do I minimize a function? Well, I take its derivative, and note I can take its derivative. It doesn't look spectacular, but I can do it. I find out for what value of sigma is that derivative equal to 0, and I come up with these things. Okay, all right, okay. So now, man, wouldn't have been nice if I got 1 out. Okay, so I have something that's a product log. That again is a named function that just has to do with inverses of exponentials. Okay, okay, all right, okay. You know what we're going to do is, rather than, now we know that this problem has some numerical part to it anyway, right? And so in order to compare it to what we get in the book, why don't we make this assumption, right, that we're working in the same units as we are in the book, right? And what I mean by that is, we know that this combination of a to the 4th, or a squared m v naught over h bar squared, that really appears in what the book calls z naught, right? In fact, z naught is like equal to well, I don't know, square root of 2m v naught a squared divided by h bar squared. Well, I can invert that, and I've done the algebra here for us, right? So I can invert that for v naught, and I get that it's equal to z naught, which the book uses in their example is 6, right, times h bar squared divided by 2m a squared. So I'm basically now choosing the same z naught that we had in the book, so that maybe I can get something prettier here. And note that I put a 6 period in because, well, I'll show you. If I don't put the period in, it gives me this expression. But product logs, remember, are just functions, and so if I force them to be just numbers, I get out just numbers. And now I see that the minimum is actually around 0.56
times A, right? So our graph up here was a little bit misleading as to, when we looked at it by eye to find out where the actual minimum of this function is. Okay, so I'm gonna, and also our choice of z naught here is different than the choice of z naught that we used when we set everything equal to 1. So what we want to do now is we want to say, well, is our energy, right, the thing that the AA plus BB plus, let me put it this way, AA plus BB plus CC, right? If I replace it with sigma goes to this times A, do I get out something reasonable for the energy? Well, I almost do, except again, it's got that V naught in it. So we're going to make this same substitution for V naught that I had here. And let's see if this will work for me. And I get 1.00497 h bar squared over 2ma squared. Okay. That has the right units, right? But is it what the book gets, right? Or does it do a good job estimating the ground state? Well, the book gets 1.81 times h bar squared over 2ma squared, which is 0.905, okay? And so we're about 10% off when we do this method by varying this function, the variational method, which isn't terrible, right? Especially because the function didn't really look anything like it doesn't really share the same characteristics that we know the ground state has. But 10% isn't really terrible when it comes to trying to estimate, for example, what your experimental parameters have to be, or get an order of magnitude estimate for what size laser you need in order to make a transition like this. And so, anyway, it's a good example of how to get close to the ground state energy, even though we know that we're never going to hit it unless we somehow guess exactly the perfect ground state wave function.
That did a pretty good job. So now let's just wrap up with our take homes. First, choose an easy function when you do this. This is a way of you want something that's normalized, you want something that's easy to integrate, and you want something that's just, we're doing an approximation method, so use your best guess as to what the approximate solution looks like. Then calculate the expectation value of the energy, knowing that expectation value is always going to be greater than or equal to the energy of the ground state, and then minimize the expectation value of the energy in order to actually do that estimate. Okay, see you next time for perturbation theory.